Yeah, please, you can continue now.
So in the Les Kessler lecture 7, uh, the Z0 and Z1 were in the literature. I mean, how do we find the omega in that?
So omega 1 procedure was, I believe, discussed in the lecture class itself. Yes. So figure 3.13, that provides one means of getting to this parameter omega.
Uh, so is it like the distance between the vertical distance of the point?
Okay, so you want me to, okay, yeah. So see here, what their observation kind of said was, the reason this single parameter was proving to be sufficient is that the different species, when plotted the way they are in figure 3.3, so let us just synthesize figure 3.3 in simple terms. So when I plot the reduced quantities in this fashion, okay, so now because I'm plotting reduced variables, if two parameter equation of state was sufficient, then I would get a single curve for all the known species. But it was observed that is not the case. The different curves do not overlap. However, so we did not get a single curve, but we get a linear curve for several species. Okay, I will not say all. Those restrictions I've already discussed for which kind of species. So most uh, likely scenario where this three parameter equation of state will work, as discussed in the tutorial also, are apolar and weakly polar species. Okay, so what was observed was that because this curve was linear, I can define one more parameter, a species dependent parameter, which characterizes the slope. So this parameter omega is an indirect way of characterizing the slope. Okay, so one option would have been I find out the slope and I define that as my parameter. However, what was done was a particular point was chosen, and that is completely arbitrary. There is nothing special about it. So that point was 1 by tr equal to 1 by 0.7. So tr equal to 0.7. And at that point, whatever was the vertical distance, that means whatever was the difference in the saturation pressure in reduced units of various species, that was given the name omega. Okay, and you can say there was some madness to the method in some sense, that at this particular point, for some variety of species, let's say your noble gases, at the special point of tr equal to 0.7, the logarithm of pr sat is coming out to be, as you can see, -1. So in that sense, you can say that that was the reason to choose that as your point. Okay, so -1 is an easy number to remember. And then we said if I'm above it, repulsions dominate. If I'm below it, attractions dominate. Okay, so yes, this omega is the vertical distance between the curve. The curve is logarithm of PR sat plotted as a function of 1 by TR, which for a variety of different species is linear. Okay, so that answers your question. And equation 3.20 gives the mathematical form of omega.
Okay, so
Did it answer or you still have a query? I believe Aditya, you asked the question, right?
yes, sir, I asked the question. Uh,
Yes. So does
there
it
was
explain?
uh, there was a question in the I was solving somewhere. So omega has to be -1 now. It's just that one.
No, no, omega is not -1. Omega is the difference between, you can say, the y-axis, which is logarithm of PR set, which is clearly written here. So the difference between the value of logarithm of PR set at TR equal to 0.7 between two sets of species. One set is taken as noble gases. So let us write equation 3.20 again. So from the figure, the way we are defining omega is it is a difference in this quantity, and because the lines are, all the curves are linear, therefore a single value is sufficient. So value of logarithm of PR set at TR equal to 0.7 for your noble gases, maybe helium, I'm not sure if this equation works, especially if you go to low temperatures. Okay, so let us remove helium from that discussion. This is how omega is defined for any arbitrary species. So omega for an ith gas is defined according to equation 3.20. And this first term, you can say the reason TR equal to 0.7 was chosen is because the first term has a kind of easily rememberable value of -1. Okay. So therefore, in equation 3.20, rather than writing logarithm of PR sat for noble gases at TR equal to 0.7, I have simply written -1. Okay. So omega is the difference in the y-axis value for your target species versus the noble gases at the value of TR equal to 0.7. Okay. So omega is not -1. Difference between these two. So omega would be 0 for noble gases, and whatever value it has for any given species, that we can then determine from, let's say, some experimental data or some other correlation. So the information required is the value of saturation pressure at TR equal to 0.7. Okay. So I can in principle do an experiment, or if I have some other means of getting this data, I will get that data. So this information needs to be accurate. And once this information is accurate, I can find out the value of omega by a single measurement. Okay. Single measurement is measurement of saturation pressure at TR equal to 0.7.
Yes. So also, what is PR sat? Is it P sat upon PC or P?
Yes, yes, yes.
Uh,
Any other questions?
Sir,
Yes.
can you please turn to page 7?
Of the same lecture, right?
Yes, sir.
Okay.
Sir, in the part where we have to calculate the critical volume, I did not understand how do we use the equation of state. I mean, do we substitute this V instead of I mean, I did not get how to calculate A and B from the equation of state and this given relation V minus Vc whole cube equals 0 at the inflection point.
Mm-hmm. Uh, so you already have, okay, so have I written equation of state here somewhere? Okay, anyways, let's assume you can do that you will go back and take a look at the equation of state. So let's say the equation of state has this particular form. Okay. And now if you expand the cube in equation 3.8, I believe. Okay, or 3.18, sorry, yeah. So we expand that cubic formula in 3.18. So let us write this as expansion of 3.18, and let's assume you get another cubic expansion, and the parameters I'm writing is alpha prime, beta prime, gamma prime, and delta prime. Now you compare these two term by term. Right? So this is the meaning of comparing term by term. And from there, you can get the parameters. Okay. So you can get the relationship which I've written at the bottom. All right. A and B. And the alternate way is written at the top. So this is the alternate way that I have these three equations. And I want to eliminate, or you can say quantify, two parameters, A and B. So I can get A and B in terms of other parameters from these three equations. Okay, so that alternate way is mentioned at the top, and this other term would require you to compare term by term to get the same answer. Okay, so this is written here also. Expand the cube root and compare with the equation of state. So this is the meaning of comparing term by term. Is it clear now?
Yes, sir.
Okay, anything else from the lecture material or anything from the problem sheets which you were not able to solve?
So is there a difference between SRK and RK equation of states?
Yes. Okay, and all these parameters. So the general form of the cubic equation of state I have given in the lecture class, and the particular form you can obtain from various other sources also. Okay, so this would be an easily available information. Of course, if I give you in the exam, I will give you the parameters. But if let's say there's a question which is asking you to use SRK or RK, you can easily obtain the parameters from the internet. Okay.
So also there was one doubt about metastable.
Mm-hmm.
Uh, in case if a curve gives us metastable liquid, then the other route will be a metastable vapor. Is it so, or they are completely
No, no.
different?
Say it again. If a curve or if an experiment, you are saying.
I mean, an experiment, curve
Mm-hmm.
experiment. If it cuts at the metastable liquid states, then the
Mm-hmm.
other route would be a metastable vapor, or they are
What
different.
do you mean the other? Oh, you're saying the equilibrium state.
I'm talking about that graph, that pressure line used to cut at 2 points, 3 points, sorry.
So you can easily visualize. So rather than I answering, so let us look at figure 3.10, right? So the green line, the green horizontal line at PE is intersecting the left branch on E. So what is E?
Uh, E was,
E is the
it should be a vapor, it should be an equilibrium, but it was told it is a metastable liquid. It was an observation, I guess. Is it so?
yes. So what we are saying is there are three possibilities at this. The middle one, or at least from the equation, there are three possibilities. Now let us go to reality. Okay. So if I look at the black, or sorry, the green horizontal line, it is intersecting your equation of state curve in 3 points. Okay. And therefore, I'm saying there are three possibilities. And what was discussed in the lecture also, the middle point is unphysical. So point number two, I have put a cross against. The left point is a pure liquid state within the coexistence region. So coexistence region is the equilibrium answer. However, within this state space, there is an alternate answer possible, which we are calling as a metastable liquid. There was a special name given to this metastable liquid. What was the name?
Superheated liquid, I guess. That one.
Superheated liquid, right? So if you go to that, I've shared a video on the supplementary reading material section, okay, visualizing metastability. So this particular experiment visualization is given in that video. Okay, this video is by Mythbusters. If you go to the supplementary reading section here, visualize metastability. So this second video, okay, superheated water. Okay, so they are telling you an experimental scenario where you can get the superheated water. Okay, so point E corresponds to that experimental condition where you have a very smooth surface and a very pure water, so distilled water sample, and it will be possible to take it above the boiling point. In this case, I'm talking that in terms of PE, so that means below the boiling pressure, and even then it will not convert to a vapor, and that corresponds to state E, which is a metastable liquid, and the kind of colloquial name we have given to it is superheated vapor. If it was water, you might call it superheated steam also, but that will be a little bit wrong. Okay, so sorry, you will call it superheated water. So superheated water in general, superheated liquid at point E, and you can see the corresponding equilibrium state, which is at 3. So what is the corresponding equilibrium state here?
Acha, it's a vapor. So
It's a vapor, right? So it's and that vapor we are typically calling it as a superheated vapor, right? So that is the answer which is given here.
so when we talked of perturbation, we meant the it goes from E to 3. Is it like that?
Yes. So when they drop, for example, some sugar cube in that superheated water, that is in some sense a perturbation, and that perturbation takes it from E to 3. Okay, alternatively, I could have just put a spoon inside. Okay, so again, I will not do that. But if you put a spoon in that superheated vapor, again, a sort of explosion will happen and you will go to a vapor state.
So is this phenomena the same as ice snow formation? Like that, for that also we need a crystal, some dust particle at the center for the crystal to start forming.
Yes, so here in this course, we don't go so much towards the nucleation and all those phenomena. But yes, so all of these are what we call as barrier processes. So barrier processes, as the name suggests, there is a free energy barrier to convert from one phase to another. So the other technical name for these processes is nucleated processes. So in these nucleated processes, barrier processes, you can see a metastable state, and that's what you are seeing here at E, because that perturbation was not available. Okay, and as soon as you provide, you are able to overcome that barrier either by increasing the driving force or by providing something else, for example, an impure particle or some other nucleation site. You are able to convert from one phase, which is metastable, to an equilibrium phase. Okay, so all phase transitions require some degree of supercooling or superheating, because all of these phase transition processes are nucleated processes, at least in the region we are discussing. There is another kind of phase transition or phase transition process which does not require a barrier. But again, in this course, we don't discuss it. I can give you the name if you're curious, that we call as spinodal decomposition. Okay, so spinodal decomposition is a barrierless phase transition. Right, any other questions, queries?
Sir, I have a doubt from the problem sheet too.
Okay.
The third problem in the problem sheet too. I actually could not visualize the schematic for the problem 3, 3.14.
3.14. Okay. So you have a tank and some conditions are given. It contains air at P and T, and volume is also given, the total tank volume. Okay. So it is connected to a compressed air line. So that's a little bit poor drawing. Okay. So this is your tank, which is connected to a compressed air line. Let us see what else is given. Which supplies air at constant P and T. So the conditions at which supply is happening are given to us. The tank initial state P and T are given, and tank is of known volume. Okay, so this much is given. The valve in the line is cracked. So there is a valve. Is cracked so that the air flows slowly into the tank until the pressure equals the line pressure. Okay, so what additional information is given to us is that the final pressure in the tank. So for all my system variables, I'm not going to use any additional subscripts or superscripts. So here my control volume I am taking as tank, and therefore I'm just representing that by simple PT. Okay, so Pi, Ti are the initial pressure temperature, Pf is the final. So Pf they are telling me has become equal to P prime if the process occurs slowly enough that the temperature in the tank remains at 25 degrees Celsius. Okay, so what is the other extreme? The process is very slow. So let's write very slow. Heat exchange with surroundings ensures temperature inside the tank is constant, only pressure is changing. Okay. The other extreme would be the process happens so quickly that there is no heat exchange with the surroundings. Okay. Under those circumstances, I might have modeled this process as adiabatic. But in this case, because the tank temperature is constant, I will assume there is heat exchange with the surrounding. That is the only way by which tank temperature could have stayed constant. Okay. So that's all. If the process occurs slowly enough, what we have to find out is Q. So that is what they are asking. So now tell me, is the schematic clear?
Yeah, yes, sir. Actually, I could not understand the third line. A valve in the line is cracked so that air flows slowly into the tank. I did not, I mean, I could not visualize how, if it is cracked, I mean, how would the air enter the tank? So,
Okay, so maybe the statement is a little, you can say, not maybe fully accurate. Okay, so I would imagine if the valve is cracked, then the loss would be to the surroundings, right? Rather than going in the tank.
yes,
So maybe let's say the valve is partially opened. So rather than saying it is cracked, it is partially opened so that the air flows slowly into the tank. So here the keyword for me is the air is flowing into the tank slowly enough so that temperature in the tank remains constant.
yes, sir. Okay, sir.
Okay. Any other queries? Any problem you want me to solve from problem sheet 1 and 2?
So in the previous tutorial session, you had solved one question, 3.25.
3 point.
Problem 3 of sheet 2.
Can come there. Tell me which problem, if you can maybe tell me the problem statement.
It was a tank wherein the internal energy and the the gas was coming in and
Okay, 3.15.
1.5.
Okay, yeah.
So in that, so what is this H prime you have taken to be constant? Like,
So here I'm using the prime superscript to denote the compressed airline conditions. Okay, so H prime, as it mentions here also, this corresponds to the compressed nitrogen flow stream. So this H prime, yeah, actually it's mentioned here. So H prime is enthalpy of the gas was nitrogen at compressed air, or you can say gas line. It's a same only nitrogen. Let's say compressed gas line conditions, and those conditions in the compressed gas line are constant. P prime and T prime are constant because nitrogen is a pure species. Degrees of freedom are 2. So from here I can conclude that all Gibbs variables, all Gibbs intensive variables, enthalpy is one of them, would also be constant. So H prime corresponds to enthalpy of nitrogen at P prime T prime. P prime T prime are not changing, therefore H prime is not changing. Okay.
but, but so in the tank the pressure and the pressures are different from the pipe now. So
No, that's
enthalpy.
okay. So we have used so this equation is actually capturing that, right? So this is capturing how the tank conditions are changing as a result of two things. So there are only two things happening here. Okay, if you look through our simplification of the energy balance, some of the things we have ignored, like kinetic energy change, potential energy change. There are no moving parts, so work is zero. So the tank state, you can say the thermodynamic state, as well as the extensive state of the tank, because moles are flowing in there, that is changing because of two factors. First factor is the flow of from outside. Second factor is exchange of heat with the surroundings. Because of these two aspects, the conditions inside the tank are changing. So yes, the tank pressure temperature are different from the compressed airline pressure and temperature. So if you look at my use of variables, I am using H prime for the compressed airline, and I'm using subscripts 2 and 1 for the tank conditions. Okay, so 1 will correspond to T1 P1, 2 will correspond to T2 P2. Because it's an ideal gas, internal energy and its enthalpy changes would only depend on temperature changes. Okay, but in general, condition 2 corresponds to P2 T2, condition 1 corresponds to P1 T1. So yes, they are different, and at no point I'm assuming them to be same. So P1 T1 P2 T2 in general would be different from P prime T prime. Is that okay? So we never assume them to be same.
Uh, okay, so so this n dot prime h prime term is not the delta m dot h term of the general balance, no? So it's a
What do you mean the delta M naught H naught term?
so the general balance which we derived in
Uh-huh.
previous class, no?
Yes.
So it's not that, I guess, because it's a minus n dot prime, and that was plus delta m dot h.
Yes, but you go to the convention in that plus
Achha,
delta, it was defined that that is the net flow out. So everything which was going out was given a plus sign, everything which was coming in was given a minus sign. So here, because there is only one stream which is coming in, no streams are going out. So all the in streams would be given minus sign. All the out streams would be given plus sign for our delta. There was a convention which was defined. Delta was the net flow out of anything, net flow out of mass in the continuity equation, net flow out of energy in the general energy balance. Okay, so therefore you are getting a minus sign in the final expression.
Yes, Subhash.
Okay, any other questions, queries, problem sheet? All right, so
Uh, so can you tell about how to read those tables of general correlation saturated liquid of the
mhm.
like
So problem 12, I will advise you guys, it's not that straightforward, so try to solve it. Okay, and once you try to solve it, you can ask me questions. And now, okay, the question is how to read the tables, the Les Kessler correlation tables you are asking.
are they the same as in the seventh lecture you gave it as a last question, no? I guess homework it was.
Generalized correlation for saturated liquids you are asking,
Yes, sir.
or the one before that, which is equation 3.2, 3.21 to get. So which one are you asking, this part?
So 3.21 I was able to get that. uh, I was just asking
Okay.
last.
So this generalized correlation for saturated liquids we are actually using in one of the problems which we are solving. Okay, so if you look at, so for liquids there are, because uh, the role of interactions is much more significant in the liquid state. So the number of options in a way for liquids is higher. The reason being, some correlation works better for one kind of liquids, other correlations works well for other kinds of liquids. And if you want most accurate information, either an accurate equation of state is required, or if you look at the propane example, very accurate tabulated data is required. Okay, so in the propane example, that big data sheet I have shared, table 7 in that data sheet is listing some of the liquid properties. Okay, so this generalized correlation is one such expression, and it is not same as Les Kessler. It is you in some sense you can say closer to Pitzer second correlation. So I will just reproduce the equation from the book. So in the textbook, there is an analytical equation given which says saturated volume of a liquid for a variety of different species can be expressed by this empirical correlation. Okay, so this is the racket correlation. So as the equation clearly mentions, it will only give you density or specific volume at saturation conditions for a liquid. Okay, so this is one such option. Other options to get to again the saturated liquid density are some accurate equations of state. So for example, Peng-Robinson is very accurate for the liquid state. Benedict Webb-Rubin, BWR, is very accurate, very well tested for hydrocarbons, liquid state of hydrocarbons. So used a lot by the oil and natural gas industry. Okay, so this is an analytical equation. And beyond that, if you want to further go to subcooled liquids, again in the lectures it is discussed. So how should I now go to subcooled liquid density? The most accurate way of doing this would be, let's say you have subcooled liquid at some P and T. Now I know that liquid properties are a weak function of pressure. Okay, so one option for me would be get the specific volume of saturated liquid at given temperature and saturation pressure corresponding to this given temperature. Okay, other way around, I could have said given pressure and the saturation temperature corresponding to the given pressure. However, then I would have needed to make a change in temperature to get liquid property, and that can lead to more errors. Okay, so I will get the liquid property at given temperature and corresponding saturation pressure. And from here now, next step would be find out how the liquid property changes from P set to P. So the benefit of this approach would be the coefficients. In this case, the relevant coefficient would be isothermal compressibility. You can assume that to be constant. So if you assume if the delta P is not too high, and for pressure, we say 50 to 100 bar is still okay. So at 50 bar, I will start thinking pressure change can affect my properties a lot. Okay. So if the pressure change is within 50 bars, I can very easily assume isothermal compressibility to be constant, and then I can very easily calculate the specific volume at the required pressure and temperature. Okay. So that is more than in some sense what you asked for. So to get to saturated liquids, there are multiple options. One option is Racket correlations. Other options are equations of state. Third option is some tables are available. And from saturated liquid to subcooled liquid, you can use isothermal compressibility, volume expansivity. Okay, depending on what kind of changes are required. Okay, so again, this last part has been discussed at the very beginning. When I talk about the liquid and solid equation of state, how to use beta and kappa to get to volume changes was discussed. Okay, so that addresses your query.
Yes, sir. And so Pitzer's second virial correlations are different from this, right? Yeah.
Yes, so Pitzer second virial as well as Les Kessler, both of those are more suited for the gaseous states. Pitzer second virial for a limited value of PNT, Les Kessler for a larger range of PNT. Okay, so again, there is a graph given in the book which tells you kind of the region of validity of Pitzer second virial correlations by comparing them to Les Kessler. So Les Kessler are more accurate, but Pitzer second virial can be sometimes easier to use because they are in terms of analytical equations, whereas Les Kessler are tabulated. This is a reason why Pitzer second virial are also finding utility. So if you're confident your PT range is such that Pitzer second virial will be appropriate, you can stick to Pitzer second virial, because the kind of species for which Pitzer second virial is valid is same as Les Kessler. So Les Kessler as well as Pitzer second virial is valid for real gases of weakly polar or apolar species. Okay.
Uh, so the only difference will be in Z0 and Z1 from Les Kessler and Pitzer. The omega will be same.
Yes, yes. So omega is a species property, so omega would be same.
But so Z0 and Z1 are also species property then for that case.
Z0 and Z1 are not species property per se. However, they are condition properties, right? So Z0 and Z1, we are only saying they are functions of PRTR. So no species dependent parameter is coming there. But you can estimate Z0, Z1 via various different or equations. Some of those equations might be more accurate, others could be less accurate. But some of those correlations would be more accurate, others could be less accurate. Okay, so less Kessler correlations are more accurate than Pitzer second correlations for Z0, Z1 in general. However, for a smaller range of PRTR, Pitzer second are almost equivalent in accuracy. Okay, so in that sense, Z0, Z1 are not dependent on species. But yes, there is a kind of species for which you can use them. If I use it for water, I will get a value of Z0, Z1, highly inaccurate. In that sense, yes, it is dependent on the kind of species. That for some species it is valid, for others it is not valid.
Hmm.
Any other questions, queries?
Sir, I have a doubt in the last problem in problem sheet 2, the problem 13.
Mm-hmm.
Yes, sir. So could you please turn to that page?
So 3.32 you were saying?
Oh, no, sir. So the problem number 13, basically the last problem in the sheet.
Okay.
Yes. So I had a doubt in the
Mm-hmm.
last line of the first paragraph, like the paths MNOP and MNQ represent two separate isotherms. I mean, how
Mm-hmm.
these two paths represent two separate isotherms? The part
So the
particularly
main.
from N to Q. I mean,
Mm-hmm.
how does this represent the same? How does it represent the same isotherm? Because
It doesn't, right? That's why I'm saying it is representing two separate isotherms.
but it's written obtained at the same temperature. Same temperature means isotherm.
Yes, but okay. So you have, let's take actual example, which might. So experiment number 1. So let us fix the species. Okay, and let us fix temperature also. Okay, now you are, let's say, depressurizing, okay, water. In experiment number 1, the end state is a metastable liquid. So the videos I have shared, they, in those videos, pressure is constant, temperature is changing. Okay, the paper I have shared, in that paper, this depressurization is being done isothermally. Okay, so that paper represents better this particular experiment. All right. So in experiment number 1, the end state is a metastable liquid, and again, this experiment is being done isothermally, and this metastable liquid, we are giving a new name also, or kind of a particular name. We are calling that as superheated water at Q. So in this particular experiment, you are ending at Q, and in experiment number 2, again a depressurization experiment at constant temperature. The end state is an equilibrium state now, equilibrium vapor at T, and this we are giving a name of. So this equilibrium state is known as superheated steam for the case of water. Otherwise, you will call it superheated gas or superheated vapor. In this case, for water, we call it steam. So superheated steam. Okay. So in experiment number 2, you are ending up in an equilibrium state. Experiment number 1, you are ending with a metastable liquid, and the reason the endpoint is different is because in experiment number 1, for whatever reason, that nucleated event did not happen. Okay, so that the free energy barrier required to surmount so that we can go from liquid to vapor state was not surmounted, and therefore I stayed in a liquid state. But I clearly know that is not an equilibrium state. Therefore, I am calling that state as a metastable state. So something which is not equilibrium, but still can be observed. So if I look at, let's say, the simple free energy diagram, let's say, as a function of some reaction coordinate, this reaction coordinate is capturing change in state. So for any nucleated event, this is at a simplest level, this is how it will look like. So it is possible, depending on the height of this barrier, that even though at this given condition state B is more stable, you still might lie in state A because this barrier has not been surmounted. Okay, but state A is not a thermodynamic equilibrium state, therefore we are calling it as a metastable state. So it is stable, but not globally stable. State A. Okay, so you can see it in practice in experimental operations, and experiment number 1 is pointing towards one such experiment. So depressurization done very carefully so that nucleation was not allowed, nucleation to the vapor state.
Yes, sir. Got
Okay.
it. Yes, sir.
Any other questions, queries?
So problem is in the beginning, how are we supposed to use the collaboration space which you created, like four, make teams of four, and
Okay,
so
let's go there. Yes. So idea is that so from each problem assignment, and some might have 10, some might have 9, some might have 12. Okay. So the idea is that each person from the team, let's say, attempts one problem at least fully. Because right now the problem what I'm seeing, or the issue I am seeing, is that you are not attempting problems to the end. And I can tell you in any course, and it's true for thermodynamics also, if you just read the problem statement and try to solve it in mind, it will look easy. You will think, okay, maybe I can solve it. But when you actually sit down and try to solve it, there will be small nuggets here and there which you don't know how to address. For example, how to get the density of subcooled liquid. Let's say your problem requires you to get the density of subcooled liquid. So in principle, you might think, okay, from some equation of state, I will get to the density of subcooled liquid. But in practice, how? How do I do that? So the idea from on this space is that this way, each person is responsible for only one problem to solve fully. That is the minimum requirement. At least try. If you're not able to solve, you come and ask me that, hey, I tried, but I was not able to solve it. So please explain this step. Okay. So the idea from my side here, I need to know specific issues you are facing in problem solving. Okay. So I can only give the bigger picture in the class. I cannot solve each and problem to the end. That is just not practically possible. So by using this, forming these teams, so let us just take example of first team, T and TK. So let's say Tanisi becomes responsible for the current problem sheet is problem sheet 3 for tomorrow. Okay. So Tanisi becomes responsible for solving problem 1, Nikita for problem 4, Tanya for problem 7, and Khushi for problem 10. And this way there will be, of course, multiple people. Okay. I've written only 4 such, but each new team will again, so this space, the fifth column, again 1, 4, 7, 10. Sixth column 2, 5, 8, 11. So that means multiple people have solved problem 1, multiple people have solved problem 4, so on and so forth. Okay. And then they can come to me and tell me that, hey, I tried this. This is one step where I am facing difficulty in solving this problem. And the hope is entire class benefits. And where that particular issue in problem solving would be discussed in the tutorial or the discussion session. So even though only one person solved that problem and they faced some issue, I'm assuming that issue might be relevant for others also, so that we end up discussing it. Right now, I am playing blind. I don't know where you are facing problems because you are not solving the problems. So where you might face issues is not clear to me. So by forming these teams, and you are then responsible at least for solving fully one problem. I am not saying solve only one problem. I expect you, because already I have synthesized the problem set to a much smaller subset. So I want each of you to solve every problem. However, for whatever reason, if you're not giving that much time, actually it's not that much time, but anyways, if you're not giving that much time, at least solve one problem fully. From beginning to end, do all the calculations, solve it fully. You can ask me for the answer in the tutorial, I will give you the answer. If you have tried to solve it fully, I will give you the answer from my side, what I obtained. Okay. And now on top of that, so that was one part. Second part was, if we want to add more interest, you can go further. So this is somewhat optional. If you want to do it, you do it. It will enhance our learning. Okay. So in addition to solving the problem, try to think how it will be relevant for industrial scale process or for a day-to-day event which you are seeing around you. Okay. So how the particular problem you have solved might be relevant in the bigger picture. Try to think of it, search for it, and then discuss in the class. So that would be excellent. So yes, I want this list to be populated. Again, this is not forced, but I expect that you take participate in this actively and populate this list so that each person in the class is member of some team. All right.
Yes, I got it.
Okay.
So
So emphasis is on problem solving from beginning to end. Yeah, you were saying something.
I was just confirming. So it is like before any discussion session, these would be very relevant because the doubts would come from the problems, right? So,
Yes,
okay.
yes, yes. So
And
before the Monday and Tuesday sessions, for that problem sheet, if you go through that, it will really help. Okay, if you can solve one problem. But anyways, you can see even today we are taking problems or questions from problem sheet 1 and 2. So I will never say no from my side. Even if you ask me to go 5 tutorials back, ask me a doubt, I will not say no. Okay, but of course, do it in time, it will help. All right. And
and
as a minimum requirement, the second thing which I've mentioned for everyone to do is each of you should at least read the problem fully and draw a schematic. Okay, that is a bare minimum you should do before coming to discussion session or the tutorial session. For each discussion tutorial session, I announce a priori which problems, which lectures would be taken up for discussion for problem solving.
okay, sir.
Any other questions, queries? All right. So the weather is warming up. So I hope that will also increase attendance in 8 a.m. class. Okay. And please take it seriously. And again, the second thing I will ask is don't trickle down. Okay. Today also at 8 a.m., there were probably two people. At 8:05, I don't know how many. But you should actually be present in the class 2-3 minutes before, not after. So what is the problem in actually coming on time? All right. So all of you, again, from my side, the only thing I will do is request. I will not enforce it. Try to be class at 7:58, 7:59. Why wait till 8 a.m. also? Okay. So if you're facing difficulty, just push your clock 5 minutes up or down. If you're facing difficulty, just push your clock 5 minutes upwards so that you can come in time. But there's no reason why you are not coming on time. Okay. If the class is at 8 a.m., come at 8 a.m. Come 7:58. All right. So 5 minutes here and there, just adjust your schedule so that you can come on time. Okay. Similarly for the tutorial, if it's 1 p.m., again, why you are trickling in at 1:05, 1:10, 1:15? So that discipline is not good. Okay. Here we are not enforcing it, but for your good, for your growth, for your time management, such kind of discipline is not good. All right. So anything else? I will close the session.